I have an exhaustive equation sheet here that you will learn how to use. I mean, all your homeworks, all your exams and quizzes, etc., you should be able to utilize this equation sheet. So it's an equation sheet that basically sums up everything all the equations we're gonna go through the textbook. And again, I recommend you solve your homework using the equation sheet. That way, when it comes to the exam, you're very familiar with the equation sheet. You're not going to bring your own equation sheet, you will use this one. Okay, so it's with you from the beginning of the semester, so you can get used to using it. I've added lots of data sheets here for devices we're going to use in the project, as well as maybe some that we're not going to use in the project but are interesting to talk about. So some power devices, some lower voltage devices, some battery data sheets, capacitor data sheets, etc., etc. All of these devices we're going to study throughout the semester. So it would be nice to, instead of just looking at stuff in the book, the ideal switch and the material in the textbook, to look at real data sheets as well. So I've added those here to the website as well. Along with, there's two very nice videos on capacitors. I really recommend you watch them. Like each one is like 10 or 15 minutes. So they're very interesting videos on capacitors, and you will really benefit from understanding what capacitors are and what the different capacitors are, and not just a symbol that we see on a circuit. There are many different technologies of capacitors, and the choice of capacitor technology depends on your design criteria. For example, we talked about ripple last time. So choice of capacitor will affect ripple. So think of a capacitor as a big bucket, right? If you have a big bucket of water and you're filling it in with water on one side, drawing water on another side to water your garden, that's your load, for example, right? If the bucket is a huge bucket of water and the garden requires a small amount of water to be put in every time, right? Are you going to see a change in the level of water in the bucket? Not much. But if the bucket's a very, very small bucket of water, and the garden is the same garden that requires the same amount of water, will you see changes in the level of water in that case? Or will they be more significant? They will be more significant, right? So, and that's capacitor voltage ripple. That is voltage ripple on a capacitor. So capacitor, you charge a capacitor, you push current into a capacitor, its voltage will rise. And that's the water level, right? So it will be important what kind of bucket we use, because let's say this bucket has this hole that is feeding the water has a little more resistance. It's sort of a smaller hole. So it's the same bucket of water, but it's a smaller hole going to the garden, right? It's more it's impedance to the flow of that water. So how does that affect? So it's the same. There's a similar effect on ripple voltage in a power supply. So we will study that, and that's why capacitor technology is important, because different capacitors have different kinds of impedance characteristics. Yeah. So we will get to that in a lot of detail later. Yeah. So just quickly, I'm not going to spend the whole class on the syllabus. Just quickly go through the rest of some of the highlights. Besides the textbook, which we talked about, there are some learning objectives that I talk about here. I think it doesn't make sense to talk too much about them in detail because you will not understand a lot of them. But the main idea is we will study the 4 conversion technologies that we discussed: DC to DC, DC to AC, AC to DC, AC to AC. We will cover all of them in a subset of all of them. We cannot cover everything that is involved in all of these type of converters, but a subset of all of them will be covered. That's basically the learning outcomes. So the learning outcomes will be divided into goals that will allow you to cover all of them, as well as the devices that we use to build these circuits, of course, as well as we talked about the filtering requirements that are needed in these circuits. That's really the summary of what we're going to do in power electronics. Let's see. This is what people like to talk about a lot. So homeworks and quizzes 5%. Well, I mean, I'm not splitting it explicitly from the beginning of the semester because I will weigh this 5% in whatever direction that allows you to get a better grade. So is quizzes going to be 4% and homework 1%, or is homework going to be 4% and quizzes 1%? It will depend on your grades, right? So I will, typically I would like to have a 2.5, 2.5. That's what ideally I would like it to be that way. But if if people are doing a lot worse on quizzes, and they need the extra points, I'll maybe make homeworks weigh 3.5% and quizzes 1.5, something like that, right? So that's the reason I do that. Same thing with the class project. So I mean, I'm doing that with the lab and the class project. So you have a lab where, typical banana plug type lab approach, where you go through all the circuits that we're going to study. You're going to go through, build them using the typical banana plugs type labs that we've used before. However, there's another class project. I'll talk briefly about the class project. The class project is not a banana plug type lab. The class project is actually a big power converter. So you will build. Does anybody know what UPS is? Uninterruptible power supply. Does anybody know what that is? So what is it?
It's basically like when there's power shortage, so that the equipment is not just turn off and on, so they can ruin the equipment. So it's like a backup circuit.
It's like a backup power supply. It's a backup power supply, but typical backup AC power supply. So if this lights in this room are probably not very critical, right? So they're probably not going to be on a UPS, right? What's going to happen if lights go down here for some reason? Kahrama loses, has a fault. There's a fault in the Kahrama power system before it comes into the building. We will lose power, right? Are we very important? I don't think so. We're okay. We have some. They want us to learn. They do want us to learn. So they were probably, but a split second loss in power is not going to affect us, right? Maybe we can just all stand up, and, relax and stretch, etc., etc. Right? So we have a backup generator, right? But for a generator to start up, it takes time, right? You will start up the generator and feed the building. So there will be a backup generator in the building. So we are sort of important. They have some backup power for us, right? But for example, the data center that we have, our email servers, our IT system, that is a little bit more important from their perspective, for example, than your education in the classroom. So they would have, and that's why the videos I don't want them to go around, because then Mark Weichel will think that I don't think education is important.
Usually the fire alarm.
Fire alarm, okay, that's a better example. Okay, so let's forget about the email stuff. Fire alarm. So the fire alarm, yes, is a very important part of the building, right? So you would not want the fire alarm to go down. So in that case, you would not depend on a generator to start up, switch the power supply from the utility to the generator to supply the building. You would have a UPS. A UPS is an electronic backup power supply. Electronics are much faster than mechanical systems, right? So a UPS can start in split seconds, and then there are many different types of UPSs. Some of them are actually online all the time. Some UPS systems for very critical, like if you're a heart patient. If you're a heart patient and you're on life support, you cannot afford for the system to fall down, right? So typically that kind of UPS is online all the time. So actually power, even when there is power coming from the grid, it's passed through the UPS to make sure that it's there. And if it's not, the UPS jumps in automatically. There's no mechanical transfer switch and then a generator starting up. A generator will start up in the hospital later. So there's typically a UPS in a hospital, for example, or UPS systems, many of them. And then there will be also a backup generator because UPS systems are based on batteries. How much battery can you put to feed a building? I mean, it's, at the end of the day, you're very limited. You cannot feed air conditioning. You will feed certain places in the hospital, maybe with air conditioning, maybe where they are very needed. Maybe, the babies, what do you call it? These boxes that they put the babies in. Huh? Incubators, sorry. So these, there's, certain things that are very critical. They would have to condition it. They would have to provide lighting. They would whatever they need to provide for. So that would be the type of UPS you choose will depend on the type of load. Again, same thing as it's a power conversion device that its design and choice will depend on the type of load. At the end of the day, what is it doing? It's taking battery energy, which is DC, converting it to AC. All these types of UPSs will be the same thing. And then they're taking mains power to charge the battery when mains power is available, right? So the function of the power conversion from AC to DC to charge the battery, and then from DC to AC to feed the load is the same. But some UPSs are direct online. Some UPSs detect when a system falls and then they come online, right? if a UPS is direct online, it's seeing power pass through it all the time, then the system will probably have to be designed for higher thermal losses because power is being transferred through it all the time, versus a system that is on standby. It's not generating power all the time, it's waiting on standby, it's not turned on, it's a different system, right? Size of that may be smaller, the losses in that will be smaller, right? The battery size in that will be smaller. So again, even though they're the same voltages, at the end of the day, the equipment will want 240 volt AC, right? And it will take in, the UPS will take in 240 volt AC to charge the batteries. But the system design will depend on the load, right? The load's requirements here. So we will actually design a UPS, small UPS, a rudimentary UPS, okay? So I have a schematic of it here, just a block diagramic type schematic over here that maybe you will understand more as we move on, right? But I will quickly go through, some of the parts of it here. So this area here is the input from the mains, okay? So typically you will have a mains input, right? That is what, 240 volts AC or 120 volts AC if you're in the US, right? And then batteries. Batteries are not high voltage. You don't buy a 300 volt battery. You typically, again, maybe if you're buying a Tesla car, then they have, I don't know, maybe the battery voltage there is 200 volts or 300 volts, but maybe it's a stack of batteries. I don't know the configuration of the Tesla's battery, but typical batteries use them UPS systems. If you've visited a UPS facility, you will find that they are 12 volts, 24 volts, 48 volts. They have lots of batteries, and there's a maintenance schedule for them, etc., etc. So what we would typically do is step down the power with a transformer. So this would be a step-down transformer to step down the voltage at the input. And then we know that the first thing we need to do with a UPS is what? Charge a battery. At the input of the UPS, we're charging a battery, right? So battery power is DC. So typically, I will have to take this AC power that's coming in and convert it to DC, right? So I will build a rectifier circuit, a simple AC to DC rectifier. We will understand how to design these. You've studied them before, I think, in 325. We will go through them again and understand how this works. Yeah. And then, so we created some DC level here, right, between these two terminals after the rectifier. Then what? We have our battery here. So between our input voltage that's DC, right, input voltage that's AC, then converted to DC, we want to put a power converter that will feed the battery. Why do we want to feed the battery with a power converter and not just connect it directly to the power supply, to the output DC here? We talked a little bit about batteries last time. We said batteries are very special, right? They like to be treated nicely, right? You cannot just put batteries in an uncontrolled environment. It will charge. For example, if a battery voltage, if this is a battery that's about 12 volts, for example, like typical lead acid battery, then if you step down the voltage from the input from 240 or 110 to about 18 or 17 or 15, something higher than 12 volts, what's going to happen? You have a higher voltage node or input, and then you have a load that's 12 volts, right? So you will be able to move current from the higher voltage to the lower voltage. It will happen. You will be able to charge it. But are you going to be able to control the current that's into the battery? You cannot. Batteries like to be charged in a controlled fashion. So batteries have something called C ratings. So it's called, C rating is typically, for example, you buy a battery that is 5 amp hours, right? A 5 amp hour battery is a battery that you can take 5 amps from for 1 hour, right? Or you can take 1/5 of an amp from for 5 hours. That's a 5 amp hour battery, right? That's how you rate batteries, yeah. So if you charge a battery with 5 amp hours, that's called C rating. If you charge it with C/2 rating, that's 2.5 amp hours. If you charge it with C/5 rating, it's 1 amp. So you're putting in 1 amp for 5 hours, right? So this is sort of, so batteries like to be charged in a certain fashion. And then if you go to the battery data sheet, for example, I think I put battery data sheet on the class website. For example, this is a battery. think if you go to the battery data sheet, and we can look at this further, and then Mu'in will help you look at some of these as well during the project. Yeah. But for example, battery lifetime here. Charging. Let's look at discharge characteristics. It's easier to. So here, if you look at discharge characteristics, not charging characteristics, so discharging characteristics, or even after, assuming you charge them, and the charging curves are these curves. I think I will go through them when we talk about batteries in more detail. But charging and discharging batteries are the same sort of issue. You have to do it in a certain fashion because it will affect the lifetime of the battery. So for example, here, this is a battery. This battery, if you discharge it to 60%, right, at retention capacity. Okay, so this is retention capacity of the battery, and this is depth of discharge. Depth of discharge is how much of the energy that you've charged the battery with have you taken out. Okay, so if you have a battery that is 5 amp hours at 12 volts, so it's 5 times 12, so it's 5 amp hours, right? Times 12 volts, that's 12 times 5 watt hours, right? So the battery capacity or energy is in watt hours. The battery rating is in amp hours. Okay, so watt hours is the energy capacity, the power capacity, power density of a battery, and then the rating, the current rating of the battery is in amp hours. Okay, so depth of discharge indicates, okay, if you've charged the battery to 100%, and you've discharged it, your load has discharged the battery to 100%, then you're only going to be able to retain 60% of this battery's ability to store energy after 300 cycles of charge discharge. Right? So I have a battery, I charge it to 100%, I discharge it to 100%, charge it to 100%, discharge it to 100%. After 300 cycles, you can no longer charge it to 100%. You can only charge it to 60% of its capacity. Right? So you will not be able to fill it with energy anymore. Right? So even though it's a 5 watt hour battery, meaning you think you can withdraw 5 watts for 1 hour, for example, you will not be able to do that. You will only be able to withdraw 5 watts or not 5 watts, 0.6 times 5 watts for an hour after 300 cycles of charge discharge. And it's the same with the charging information. So, but if you discharge the battery only to 50%, then this battery can last, 550 cycles. If you discharge only to, I don't know, 30%, then you can use it for 1300 cycles, right? So the indicator on your cell phone battery, right, is not an indicator of your battery being 0% discharged. Because if it's 0% discharged, then they are discharging 100% of the energy in the battery, right? If they do that, then the lifetime of the battery will be very short, right? So I don't know what they've set it for. I mean, I have no clue, right? But it depends on, it's a design criteria, right? They will choose the lifetime of the battery. The designer, the designer, will choose the lifetime of the battery based on what you exchange with the user. You tell the battery is finished, and you shut down the phone. But is really the battery completely depleted? I don't know. I cannot tell you. It will depend on the design criteria, right? Because I can put this indicator at anywhere, and as soon as there is an indication of battery discharge, the voltage will go down, for example. So you can measure that and turn off the cell phone, right? So it's a design criteria, right? So I don't want to just put the battery across the rectifier, the DC input. I would like to put a controlled voltage source in there, so that I can charge the battery at a constant rate. Because the same thing as discharging, charging at a constant rate allows you to understand the lifetime of the battery. It will allow you to say, okay, this is my design. This is what I'm doing from a design perspective. I'm not just throwing things out in the air. So here what we did was we've put a linear regulator. We talked about linear regulators last class. We said that they are horrible, right? Because they are going to do what? What does a linear regulator, why is it very bad? Linear regulator, linear power supply? There's a lot of power loss. So you're depending on what? You're depending on, this is a device. It's called a linear regulator. It's a 7805 or 7812, right? It's a 7812 device. LM370 device. It's a device. I have the data sheet on there. So it's a device that basically is acting like a linear regulator. So it's like the MOSFET linear regulator that we discussed last time. Very similar to the MOSFET linear regulator. It's put in series with the load. And then there's a lot of other stuff that allows it to work, right? We said that the MOSFET, we talked about this last time, requires a power supply between the gate and the source to make it work, right? So this other stuff that we've added here is sort of this box that I drew last time as the power supply between the gate and the source that allows this block here to work as a linear regulator and supply the battery in a controlled fashion. In this case, I think we're putting 1 amp only through the battery, right? So everybody gets that? So we know that this is bad design. This is very bad design, but we added it in there intentionally, right? To make our life easy, as well as to say that we're teaching you something, okay? So no, it's not a good design. And the power, I mean, this is somewhere where I don't care about power electronic noise, or switching noise, or changes or ripple voltage. I don't care too much about it here, right? But I mean, it's easier because the board then becomes a nightmare to build, as well as it's educational because then you understand, okay, linear regulators. This is how I use it. This is how I design it. It's in there. So now I'm supplying my battery. Right, so I supplied my battery with a constant fixed current, and then this control circuit here, sort of disconnects the stops the charging whenever you've hit the limit of the voltage. So it's a small sort of control circuit. The data sheet of the LM device will tell you how to design it, right? And then after the battery, so we have DC at 12 volts, right? Our objective is to feed a load that's 120 volts or 240 volts. Right, so we have DC at 12 volts now. So what do we do? Exactly. So we want to step up the voltage. So there are many, many types of step-up power converters that we will look at. The simplest ones cannot be used in an application like this, mainly because of the simple boost converter that we will talk about later, for example, has a step-up ratio of about maximum practically 4 or 4.5 maximum. So practically I cannot do that. So if I take 12 multiplied by 4, that's 48, right? I'm not at my 120 volts, or I'm not at my 240 volts, right? So I have to find another alternative. That's how you choose different types of step-up converters, right? There are many different types of step-up converters. We will study a few of them, right? Some of them have limitations, so you have to choose others. So we will not study all of them. That's why you will have to understand that there are step-up converters. There are a family of them. You study 2 or 3, then you have to dig up the rest, right? If you have other limitations here. So this section here, this block, as well as this block, as well as this rectifier block and this filtering block, they all do the function of stepping up the voltage from 12 volt DC to 180 volt DC. Here I'm creating only a 120 volt AC output. Okay, so what is this whole section? What does it practically actually do? What it does is actually it takes this DC and creates something like a square wave at high frequency, right? Because I would like to be able to step up the voltage, but I cannot use the simple circuits that we will talk about later. One good way to step up and step down voltages is what? Something we've talked about here at the input. Transformers. You've studied transformers in 338, or if you haven't studied them, you probably heard about them. Transformers are a great way to step up and step down voltage. Great way. The problem is they don't allow you to push DC through them. We will talk about that later, why. Okay? You cannot step up or step down DC voltages through a transformer, because transformers rely on an alternating magnetic field to be able to do their job. And we will go into that in detail when we talk about them later. But for now, because they rely on this alternating magnetic field, then I have to be able to put an AC voltage at the input of the transformer to get an AC voltage at the output, and then I can rectify that. That's exactly what I'm doing. So I'm taking the DC voltage and I'm chopping it up. So I'm doing a DC to AC conversion. DC to high frequency, AC to AC conversion. Why high frequency? Because we said last time briefly, and we will understand why later, when you increase the frequency of a voltage or a current signal that you push through a transformer, you can use a smaller transformer for the same power rating. We will talk again. We will come look at the design equation in more detail. But basically, if you increase the frequency, then you can use smaller magnetic components for the same amount of power. Take it for now that, and we will look at the equation later to show you that. So after I create this high frequency AC, I'm rectifying it, which is what we did at the very beginning. So I rectify it to create a DC voltage, and because I have all this ripple stuff that we talked about last time, I added a filter here. Okay? So then I get my high voltage DC, 180 volts DC. Now with 180 volts DC, I can take this 180 volts DC and use a DC to AC converter, or DC to AC inverter in this case, to create my output AC voltage. So this DC voltage here goes where? All of this is some control circuits. That's, up for changes. It's just a block diagram for now. Just a block diagram for now. All of this, some sensing circuits, etc., etc. Just a block diagram for now. The main power electronic circuit is here. So this circuit takes in the 180 volts, right? And uses an inverter circuit, a DC to AC inverter circuit, to produce the 115 volts AC at the output. Okay? So the rest of the circuits here, we said that all these devices require a means or a circuit to drive them, right? A gate voltage, a gate to source type voltage. So the rest of some of these circuits are what? Some of these circuits are the gate drive circuits. So these circuits would be sort of gate drive circuits. So there will be a big bunch of the circuits that we have on the board. They have to be gate drives, because all these switches require specific gate drives, right? And then of course there are some sensing circuits as well that you will have to see. So as well as control circuits. So again, these gate drive circuits will come from sort of coming from here, but they condition the gate drive signal that's coming from my controller, right? So I will have a control circuit that is maybe an analog control circuit that we see here, and we will talk about this analog control circuit. It's a modulation technique. We create some sort of modulation method to change this DC voltage to an AC voltage, right? So we will talk about more of that later, but basically this is the rest of the circuitry that you will see on there, right? So this is a summary of your project, right? After 8 break, you will start on your project hardcore. Like there will be, every week you're expected to work on your project and give Wayne an update. At the end of the semester, there will be a report on your project. So you will be expected to write a report on your project. The report should include simulation waveforms. So you're going to be simulating all the circuits that you see here, and you will be verifying the simulations with experimental work, putting all of that in a nice report, putting the relevant equations from the class that we've taken that verify, that go through this material, and you will build the whole thing. So the transformer will actually go in and wind the transformer. And, how many turns? 130 turns. So you'll count the 130 turns. It's a bit annoying, but it's you're going to go through the whole design process. Okay.
Are you going to work on the project during lab sessions?
You will have some lab sessions where you can work on the project, but I don't expect that it will be done only in lab sessions. You may need to. You should be able to. You should be able to, but you may need to go more to put some to get it done. Yeah. So you will not lay out the board. So the good news is we will buy the components. I'm not. I hope I didn't scare you all. So we will buy all the components for you. So you will have all the components ready. The PCB boards, the circuit boards, will be ready for you. So we've already designed the circuit. We've built the boards, or we're finalizing the building of the boards, some of the boards now. But we'll give you the boards, bag of components. And then you will have sort of guidance to, we're going to study rectifiers in class. You go build the rectifier. We studied the linear regulator last class briefly. You go and build the linear regulator, a portion of the circuit, right? So you build portion of the circuit as you go on, and you write reports on the circuit as you move on. I think that's better than if you wait until the end to write the report, it's not going to happen here. So it's it's a fun project. We don't get, I mean, again, we're not designing every single component in there and every single circuit. I mean, I used to make the class design it, like not just, build it. So right now I'm making you build it based on, okay, we've learned how rectifier works. We've learned how an inverter works in class. We've done some homework examples on some examples in the book, but we actually don't go through the design details, right? So we go through, some of the operational details, but not the design details of everything in the schematic. I used to make it. I used to be able. I used to do this, and the students were stopped. I got so many. Okay, you guys, you're crazy. You're making us do too much work, kind of thing. So I stopped doing that. But the students still like the project. So they like the project, but they don't like too much work involved in the project. So what we did was sort of something in the middle. We give you the circuit board. We give you the bag of components. You have the design. We will give you the design. You have to build it as we go on based on what you're studying in the course. So you still benefit. You don't get the 100% benefit. You get like a 75% benefit. If you want the 100% benefit, come to me and I'll work with you to design the whole thing in detail if you're interested. But that's out of the scope of the class. Okay, so this will be your project here. So that's equation sheet, your project. As I said, some data sheets in there. Syllabus, let's continue on with the syllabus. So that's the project. We will have 2 midterm exams. The dates for the exams are already, I put them on the, tentatively at least, I've put them on the lecture schedule. So tentatively, there will be an exam on October 12th, and then another exam on November 25th. So these will be tentatively your 2 exams during the semester. This is Eid break. I just found out that I may not be here also the week after Eid break, so we'll see what happens. I'll modify that accordingly. But this will be this is the latest as far as I'm concerned lecture schedule here. And the lab schedule as well is here. So next week you do have a lab. So next week there is the first lab, basically introduction to the simulation tool that you will use to verify all the circuits in your project. So PSpice, Ma'in will go through that through the simulation tool with you, so you're more comfortable with it, as well as introduce you to the various equipment in the lab. Maybe talk a little bit more about the project, show you maybe a previous or some of his work on the project, etc., etc., etc. So every week we will have a lab. If it's not a regular banana plug lab, it's going to be a recitation. If it's not a recitation, it's working on your project. Okay, so every week we will have a lab. I mean, Ma'in will be available every single week. You should make use of it. If you do make use of his presence and work in the lab, then you should finish your project on time. You should be okay, right? I don't think there should not be anything to worry about, right? There are labs where we're gonna just devote to the project. So all of these labs are devoted to the project here, right? There are labs that are devoted, but you can start before that and you can finish before that if you wish. I don't have a problem. So it's up to you really. But this is the tentative lab schedule. What else? I think that's it for now. We'll get started. So we started last time working a lot on chapter 1. I want to go through a little bit of something outside the book a little bit, and then we go back to the book. Just a few examples of block diagrams of power converters, and then we'll go back to the chapter 1 slides. Yeah. So I will go through the slides typically in a lot of detail, stop and explain on this desktop for a while. That's the approach I will typically use here. So just before we move on, so I would like you to build some power converter architecture. So like if you have a cell phone, for example, and typically the cell phone, you would like to charge it, right? We said that the voltage here is what? 240 volts, 50 hertz, right? So I have a 240 volts, 50 hertz. 240 volts what? Peak, RMS, average, RMS, right? So we know that anytime you talk about voltages, it will typically be RMS. In single phase systems, it will be typically RMS for single phase. But if you are talking about a power system, not a single phase, if somebody doesn't specifically say single phase, then they're probably talking about three phase, and they're talking about line to line voltage RMS. That's typically what they're talking about. If they are specifically talking about single phase, it's going to be single phase RMS, of course, yeah. Right, so it's 240 volts, 50 hertz, right? And then we said cell phone batteries are typically what? 3.7 volt lithium ion batteries. That's almost all cell phones here. Right? So how do I go from here to here? I want like a block diagram. What sort of blocks do I need to fit in there to make this happen here? The blocks out of the 4 blocks we talked about. We talked about what? AC to AC blocks, DC to AC, DC to DC, and AC to DC, right? So that's one way to do it, yes. So I can put a AC to DC and converter, and we call those what? What was the other word for that? For those? Rectifiers. The inverter was the other way around. From DC to AC was the inverter. From AC to DC was the rectifier. Okay, so this is an AC to DC rectifier. And now you have something similar to the project where we have an AC to DC rectifier that is producing some DC voltage. Maybe I put a transformer here to step it down like I did in the class project, or maybe not, right? In any case, we have a battery here. We said batteries like to be treated nicely, right? So typically before a battery, we will also have to have a converter. What kind of converter did we put in the project? As a block, what was the function of the converter? It took what? Took this rectified step down AC volt. After we rectified it and stepped it down and rectified it, it was DC, right? It was DC, but coming from AC, right? It was AC coming in after a rectifier, and we had some DC at the output of that. That DC was, coming from the AC supply. Is the AC supply, nice, fixed, controlled? No, it fluctuates during the day. If you've taken the 459 power systems course, you know that it changes during the day. Slightly, but changes during the day. Right? It can change a lot, but for the most part, should change slightly. So after that, because I have this DC that's changing, it's not going to be nice for me to put the battery right across it, right? So I need to put what? A block diagram here that will take this DC and convert it to a controlled DC. Right? So if I would need a controlled DC output to be able to connect to a battery. That way, if my battery is 3.7 volts and I've put in 4.7 volts, and then there's, the batteries have impedance. These wires have impedance. So depending on the difference in voltage and the impedance, current will flow. Right? So you can put in a DC to DC converter here that can control how much current is coming out of this DC to DC converter. Okay? So you need that. Otherwise, you cannot charge your battery nicely, properly. You will ruin your battery, basically. So this is called the power converter architecture, right? One thing to note about this architecture is that the power that's coming in from the supply and going to my battery is passing through this stage or this box, and it's passing through this box as well. Correct? It's passing through two boxes. This box has an efficiency, 1. This box has an efficiency, 2, right? So what is the efficiency of the power conversion stage? Some? Think. It's a product. It's a product of both, right? So you have this has a power conversion efficiency from here to here of 80%, for example. Now, after 80%, you have another converter that has another 80% power conversion efficiency. So the sum of the efficiency is, total efficiency is efficiency 1 times efficiency 2, right? So if this is 0.8 and this is 0.8, then we're talking about the efficiency of the system for what? What's the full efficiency of the system? If each of them is 80% efficient. Oh no, 0.8 times 0.8 is what? 0.8 times 0.8? What? 0.16, right? Huh? 0.64. 8 times 8 is 64, right? Yeah, yeah. So it's 64%. So we're talking about a 0.8 times 0.8. We're talking it's equal to 0.64. So we're talking about 64% efficiency, assuming each stage has an 80% efficiency. So is that good?
It's not terrible.
It depends on what you're building and who you're building it for, right? If you're buying a cheap power supply, you know that you're not getting something valuable. I mean, if you're Apple and you want to make this as small as possible, then you know that you cannot live with that. Okay, so it depends on who you're selling it to, how much you're selling it for, who's building it, all of that kind of stuff. The knowledge of the customer, yes.
Professor, in this design, how about we have a step-down transformer to begin with that converts the AC to DC, and then we have that converts the AC to AC that steps it down, and then we have another system that converts the AC to DC. That,
Sure, you can do that.
so there are multiple designs for this, right?
There are multiple designs. That's what there are multiple. That's why when Khan said, Khan, right? Your name?
Connor?
Connor. Yeah, you said Khan. That's why when Khan said this is how you would do it, I said this is one way of doing it, right? So yes, this is one way of doing it. Another way of doing it can be as an AC to AC conversion. So bring down the AC to a lower value. And this AC to AC conversion, in this case, for example, in this case, I assumed that I can live with maybe a simple AC to DC rectifier, maybe uncontrolled rectifier here. Simple, very simple, uncontrolled topology. That is producing some DC that is not controllable. I can go with a more complex DC to AC to DC converter topology, by the way. I can go with a completely more complex AC to DC converter topology and eliminate this. Right? You can do that, right? But it's a more complex topology. Is this more complex topology going to have a better efficiency or not? You will have to study that, right? Probably yes. Probably from a system efficiency perspective, single stage topologies or single stage power conversion topologies are more favorable. And that's a lot of the research that's going on. For example, power electronics people, let me give you an example of where that is actually happening considerably. So you have a PV panel. Right? This PV panel is giving what sort of output? AC, DC? What does the output of a PV panel look like? Is it an AC output or is it a DC output? Bless you. No, it's a DC output. So outputs of solar panels are typically DC outputs, ranging from, let's say, 12 to maybe 48, right? I would say, depending on the number of cells. So each of these cells produces some DC output, and then they string them in series and parallel to produce the panel, right? So 12 to 48 would be the voltage. So let's say you have a 20 volt DC output. What do you want? Where do you want to send this typically? Maybe to your house. Plug it into the grid, right? You have a grid connected home, you have your PV panels on top, and you grid connecting your house, right? So you want to send this maybe to your, you have 3-phase at home. Typically, you would have a single phase connection, especially in the US. Here, I think we have 3-phase coming into the house, each house, yeah. But in the US, we either have single phase low power, which is 110 volts, 60 hertz, or we have single phase high power, which is 240 volts. So they take the transformer terminals, each 110, and it's 220 volts, high power connection. That they typically connect the washer dryers. In the washer dryer rooms, correct me if I'm wrong, but in the washer dryer rooms, they would typically have these higher power connections, yeah. So it's a 220 volt connection. They just take the two phases. So they take a 110 connection, another 110 phase, and they just feed the power from 2 phases. So they have a 220 volt connection. So, but typically, let's say we're talking about 110 volts, 60 hertz. So, how would I connect these? This is 110, this is 20. We said that the simple DC to DC converter topologies don't have the ability to step up voltage except maybe 4 times. So 20 times 4 is 80. So I cannot use a simple DC to converter, but I can use a more complicated DC to converter. Yeah, I can use a more complicated step-up topology. I can use that, but how do I do this then?
Inverter, DC to AC.
So you want me to put a DC to AC converter here?
Or you could step it up first, DC to DC, and then
So if I can do this, or yes, I can do, this is the PV panel as well. I can take this, my PV input, and I can step it up, DC to DC, step up, right? And then
DC to AC.
I can put a DC to AC inverter to my power supply. This is one way to do it, this is another way to do it, right? You will see that in our project, for example, we have a DC to AC high frequency converter stage, not like this. This is a DC, this would be a DC input, 20 volts, to 110 volts, 60 hertz output, right? You can probably build that. And that's where a lot of people, there's a lot of work on, single stage power converter topologies related to photovoltaics. That's one of the hot areas that over the past few years, people have come up with so many topologies for DC to AC inverters, for PV applications that are single stage, meaning one conversion powered stage instead of two. This is the classical way of doing it. This is how people have been doing it for a very long time, right? The past, I would say, 10 years, there was a lot of emphasis on this. And this is sort of the de facto in low power applications.
Isn't that what they're using, like, to go from your cigarette lighter in your car to power, say, a TV that you put in your car for the kids?
They would do that. Whether they do that, a single stage or it's a dual stage, I don't know. I would think that these cheap ones would probably be dual stage converter topologies, classical converter topologies. I would think so. This mainly came to life because of what's called microinverters in in photovoltaic applications. There is this interest in extracting as much energy as you can from a PV field, right? Photovoltaic field or photovoltaic array. And the best way to do that is to put an inverter in every panel. That's in a short way of, in summary, that would be probably the best way to do it. The most energy harvesting that you will get is to do that. Granulize it to the smallest granule, right? Extract as much energy from this module, from that module, from this module, and that module. The other way to do it is, of course, to put all these modules in series and parallel and connect them to a big central inverter. That method has issues with when there's shading, when there's different types of panels. We will not get into that in this course. But because of that interest to extract as much energy as you can from a PV module or a PV array, people are working on what is called a microinverter. So it's a small inverter that they plug into the PV panel, right? And the benefit of that is you're extracting as much as you can from that PV panel itself. The drawback was people started using these topologies and it wasn't very efficient yet, right? And then because this inverter has to be as small as possible, has to be efficient because it's plugged into the PV panel, which is put in the field. It's not put inside the big substation with air conditioning, etc., etc. Then people wanted to make sure that it's as efficient as possible, as small as possible, as cheap as possible, because there are so many of them, right? So people worked a lot on single-stage topologies for that purpose. So this really came to life over the past 10 years, I would say, because of PV applications, right? This is another way of doing it, right? So there's no right or wrong. There's no right or wrong. There's a spec. So, okay, another application, camera flash. Camera flash, your camera typically is running off a 3.7 volt lithium-ion battery, right? Typically that's what it's running off of. And then typically camera flashes are sort of capacitive type loads that are very high voltage. So you basically need a power supply that will take this 3.7 volts, extract a lot of energy, and then dump that energy in a capacitor. What do I mean by dumped energy? What's energy in a capacitor equal to? From your 214 course? Half CV squared, right? That's energy that you can store in a capacitor. So you take that energy, and the idea is to dump it into the flash circuit. So you give a huge amount of energy to that flash circuit, and it will create a great flash, right? And the way to do that is, of course, increase the voltage on the capacitor, right? So it's a step up topology. So I need to take this 3.7 volts and step it up to hundreds of volts, right? So how would you do that? This is DC, and this is DC as well, right? So how would you do it?
DC step up.
Sure. So I can put a DC to DC converter, step up. What does this look like? There are many types of DC converter step-ups, right? We will study some of them, right? One of them is what we have in the project. This through an inversion stage with high frequency. That's one way. The other way, there's a simpler way that we will study in more detail in the class later in chapter 6. So that's something that you would need to do. So you would typically have a switch here. Of course, you want, whenever you charge the capacitor, you have your camera flash, I don't know, somewhere here. After that, sorry, put the switch after the capacitor. So you first charge the capacitor with your power supply. When it's charged, a switch will close to connect your capacitor at very high voltage now to your flash. And you will ignite the flash and take the picture here. So that's another application. So another application, electric vehicles. You have, typically in an electric vehicle, you have maybe a battery that's about 300 volts DC. And then what sort of load do you have in that case? In an electric vehicle? You have a motor type load, and it's typically a three-phase type motor. So three-phase motor. So this is your input, and this is your output. Motor voltage, maybe, I don't know, 400 volts or 300 volts. AC. So it's an AC voltage, yeah. Yeah. All motors that are used in electric vehicles would be AC. So there are some, those hobbyist type websites where you'll find, they will give you a conversion kit. You can buy a conversion kit for your car. Some of those may be some DC motors, maybe. But industrially, they would not use DC motors because of in hybrid vehicle applications, mainly because of the brushes, right? So they have brushes that wear out. It's not something convenient, yeah. Like the car's dynamo that is used to charge a car battery. It's based on a sort of a DC type machine with brushes, right? The alternator. So it has brushes, right? These brushes wear out with time. They take a long time, but all they're doing is charging the battery, right? So the load is not very high. But the motor that's driving your car is a much bigger load, right? If you imagine having brushes in there, they would probably wear out a lot faster, so people don't want, the reliability is an issue, one of the main reasons, yeah. So other types of motors. You've studied, for example, induction machines in Dr. Haytham's class, in 338 course, and then you've studied synchronous machines. So it's either a permanent magnet type synchronous machine or an induction machine, okay? So typically a permanent magnet synchronous machine is more common nowadays, yeah. At least for example, the Prius uses a permanent magnet synchronous machine. The Honda uses a permanent magnet synchronous machine. The Tesla uses a permanent magnet synchronous machine. So all of these use permanent magnet synchronous type machines, yeah. So three-phase permanent magnet synchronous machine, some AC voltage that's high, comparable to 300 volts. So in this case, how would you do this? What do I need to do? Convert my DC to AC. This AC is what? Is it a fixed frequency? That's a good point, sorry. This is AC. Is it a fixed frequency like the grid? It's not a fixed frequency like a grid, right? It's variable frequency AC, right? Because motors, for you to change the speed of a motor, you have to change the V over F profile, if you remember for 338. Or basically you have to, if you didn't take 338, you have to change the frequency to be able to change the speed of a motor, right? So you need to produce a variable frequency AC and also variable magnitude AC. Variable frequency and magnitude. And variable magnitude AC. So to do that, you will put in here a DC to AC conversion stage or an inverter. Okay? So and this one would be input would be DC and the output would be three-phase AC. We will study that in chapter 8, right? So we will study all these topologies in the different chapters, examples of all these topologies in the different chapters. Last one, I have a wind turbine. This is my wind turbine, flower. Wind turbines are what? Typically, they would be similar to the electric vehicles, also induction machines, or permanent magnet synchronous machines. So it would be a three-phase machine in any case, right? That would be the input. The AC output, is it going to be fixed frequency? It's going to be variable frequency. Is it going to be fixed magnitude? Variable magnitude. So it's going to be variable frequency, and magnitude AC output, AC from here. And then, where do I want to typically pump this at the end? Into the grid. So I would typically have a three-phase grid here. That is what? Is the frequency into the grid variable? It's fixed frequency, so it's fixed frequency, fixed quote unquote, because when you take the 459 course, you understand that it varies a little bit. Yeah. So fixed frequency and magnitude, AC. Right. So now, what do you need to put in there? No, but this is variable frequency and magnitude, and this is fixed frequency and magnitude. So if you just filter, you will filters will remove high frequency content. But this is a nice clean content, right? It's a generator that's just spinning, so it's a nice clean AC output. Yeah. You can do AC to AC, sure. So you can do a AC to AC converter. That's one topology. I agree. Industrially, this is never used. As far as I'm concerned, this is not used at all industrially because they're very complex. The AC to AC converters are very, very complex. The number of switches is huge, and they require, or they would benefit from the existence of a bidirectional power switch. There is no bidirectional power semiconductor. There's a lot of research. I don't think there's a commercially available bidirectional power switch as such. So a MOSFET.
They just use a transformer.
A MOSFET moves current in one direction, and voltage is in one direction. If you flip the voltage, the MOSFET will not work. Current cannot go to that direction because there is a parasitic diode. Even if there's no if the voltage is flipped, you will not be able to control things because current will just flow because of the diode. Even if there is no diode, current cannot go through in reverse through a MOSFET. Right? So there is no bidirectional switch. So what did you say? Sorry?
They just use a transformer.
But what does a transformer do? Transformer converts AC at the input to AC at the output, sure. But this would be high voltage AC to low voltage AC, right? Or vice versa, low voltage to high voltage, right? The transformer is a constant power conversion device. So you put in a certain amount of power, you get the same amount of power, assuming there's no losses. So if you put high voltage in, low current, you will get low voltage, high current.
So they have to switch it to DC to get a constant source and then switch it back
Exactly.
to DC.
That's the workhorse of the industry. Take this three-phase AC, convert it to DC using a three-phase AC to DC converter, or what is it called? What's the other extra word that the power electronics people use? Rectifier. So it's a three-phase rectifier. So take this variable frequency and magnitude AC, convert it to DC. And then now you have DC. You could take this DC and convert it to three-phase AC, pump it into your grid with an inverter. Okay,
So that's easier and cheaper to do than doing an AC to AC?
I mean, that's what's used in industry, so I'm assuming it's cheaper, right? So researchers like to, create problems and solve them, right? So maybe during the time that they create some problems, they create a useful problem, and then when they solve it, then it's a useful solution, right? But typically, again, that's why the recording of videos is a bad thing, right?
So in
Well, when you put DC, finish. You took your AC, variable frequency, variable magnitude, right? And you converted it to DC using an AC to DC controlled rectifier. We will study that as well. We'll study one topology to do that, right? So there is a way to do that where you're able to control your output DC. So even if the input voltage is varying, you'll be able to control the output DC voltage. Within a certain limit, of course. There will be that's why wind turbines, for example, have a cut-in speed. Because beyond a certain limit, for one of the reasons, right? Beyond, I mean, there are reasons due to the aerodynamics, and there are reasons due to the power conversion, right? So you cannot design a power converter to work in all operating conditions. Otherwise, it's going to be, if you have a very high voltage and very low current, that's one condition. If you have a very low voltage and very high current for the same amount of power, that's a completely different condition, right? So you can design a power converter to operate within a certain range of conditions. You have to know your conditions, and you have to have protection circuits to stop the power converter from operating outside these limits, right? So that's, all of this stuff is something you will have to do in power electronics. As a power electronics engineer, you will have to consider all of these things, yeah. So this is, okay. So everybody's okay with this? So we will study all these topologies during the course of the class. Or topologies that can fit in all these boxes, okay? But there are many ones that we study that are not as good as others, right? And I will tell you, but I cannot cover all of them. So for now, we will go back to the slides. I think we covered most of the material in the slides, but I'll skim through it a little bit quickly. So this is chapter 1, and we talked about the four conversion topologies, four conversion architectures, that we will be studying throughout the text. And basically, they connect sources to loads, right? And you have to typically know your loads and sources to be able to design whatever's in between, right? So you have to know them. As I said, from AC to DC is called typically rectifier, and from DC to AC is typically called inverter. That's just terminology. We discussed that, and then we talked about the fact that we can have two blocks in series, for example, helping in the conversion, versus one block. And we talked about the drawback of that being the lower efficiency, because you're multiplying the efficiency of both blocks, right? It may be easier, or it may be more practical, like in the wind case. It's more practical to do this two-block conversion versus a single-block conversion. It's more practical because of the limitations in current technology. If people develop a bidirectional control switch, the AC to AC converters will probably be the best, probably. But if people don't, and we're living with whatever we have today, then we cannot. And they will not be the workhorse because of complexity, efficiency, limitations, etc., etc. We talked about this basic power converter, right? This potential divider is a basic power converter topology that we talked about. From 9 volts, you know that if this is your load and you know RL, you can produce 3. You will choose this R, right? You know that you can do that. The drawback is the losses. We talked about that in the last class. And we talked about our alternative. Our alternative in power electronics, okay, remove this resistor and don't put a classical MOSFET, linear type MOSFET circuit, and operate the MOSFET in saturation and cutoff regions and make it look like an ideal switch, right? We talked a little bit about that, and we said that the way to do that is pulse this input voltage so that the average output is the 3 volts that you require, right? So you would write the average equation for this waveform, and the book goes through that, and they do the derivation here for you. So and so the output here would be 3 volts. So from there you can decide what did we call the turn on time versus the full period. What do we call the time that the switch is on during the switching period? We called it T on, but what did we call? We called it's a duration. We called T on was the time it was on, and then as a percentage of the full switching period, what did we call it? It was a percentage of the full switching period. We gave it a name. Duty ratio. Remember that? No? Duty ratio, duty cycle, duty ratio or duty cycle. So the amount of time the switch is on, guys, come on, no, you have to. It's the amount of time the switch is on versus this is my full switching period. The amount of time the switch is on versus the full switching period, or the switch is off versus the full switching period, is called duty cycle or duty ratio. And it's typically given as a percentage, right? Or it's given as a a tenth as a part of a one, basically as a ratio from one. So we said that it's the turn on duty cycle, or the on duty cycle is T on over TS, which is the switching period. Or the off duty cycle is the T off over TS, right? That's the off duty cycle or the on duty cycle, right? So it's important, the terminology is important, yeah. So what if I keep the switch on for a longer period of time? What's going to happen to my output voltage? Right? The average will increase. Right? The average value is basically the area under the curve. Right? The area under the curve. Right? So if you increase the duty ratio or duty cycle, on duty ratio, on duty cycle, then the average voltage will increase. That's how you control a power supply. That's why you add a controller to it, because sometimes your load wants 3 volts for a while, and then it wants 3.5 volts for a while. Then it wants 4 volts for a while, for example. Right? Like a battery charging application. If the battery is a 12-volt battery, when it's discharged, it may be at 11 volts. And if you want to put 1 amp through it, and you have a 1 ohm impedance, then you have to make the difference between the two voltages 1 volt. Right? But what if the battery voltage goes up? You have to make sure that your voltage also goes up, otherwise your currents are going to go down. Right? So you have to control the output voltage of a power supply. So there will be a typical control circuit. We will not get too much into the control of power supplies. Again, that's a big area as well that we will skim through briefly. But we will learn a little bit about it. So who has taken 420? You're taking it now? Nobody else took 420. Yeah. So, but you've taken 214, and at the end of 214, you were doing some Laplace circuits, right? Laplace derivations of circuits, right? And you were finding transfer functions between inputs and outputs, right? In control, what you do is you take this transfer function between input and output, and when you know that transfer function, you should be able to add a controller that will allow you to control the output to do whatever you want. So you have an output, and you sense that. That's the control class. You take that output of the transfer function and you sense it. After you sense it, go back to the controller. Okay, this is the output. This is the system. What do I want it to do? Something else. Okay, so how about give it a push in one direction? So the controller will change the duty ratio to push it in the right direction. Push what? Push the system, whose transfer function you've derived in 214. That transfer function can be a circuit, or it can be a motor, it can be something else, a full power system, right? So that's the 420 class. So in here we will sort of, what you did in 214 for linear circuits, we will do for power supplies as well. So we will make the power supply look like the linear circuit and derive its transfer function. And then you go to Dr. Hazem and you can take the 420 course and say, okay, I have a circuit with a transfer function. How do I control it? He will teach that in a lot of detail. We will briefly skim through it. Okay, so that's where we sort of hand over to the other class. Yeah. So, and then we talked about adding the low-pass filter. We said that, okay, we want 3 volts DC. We don't want an average value. So what do we do with this waveform? Khan said, add a filter. And that's exactly what we do. We spend a lot of time talking about filters. That's why I put data sheets for capacitors, inductors. I put the 2 videos for capacitors. It's important because capacitors are part of the filter. And the technology of the capacitor will affect how you design it. Of course, there's a loss due to the low-pass filter addition, which is going to contribute to the efficiency loss. But compared to a linear regulator, here I have an ideal switch and I have a low-pass filter. I'm not depending on dropping my voltage across my linear regulator. Like in the linear regulator, I was depending on dropping a full voltage. I have 9 volts coming in, I want 3 volts at the output. So I was intentionally putting a voltage drop of 6 volts across my linear regulator. With 1 amp flowing through it, power is V times I. 6 volts times 1 amp is 6 watts. I'm dropping that 6 watts, and this device is burning 6 watts all the time. Versus here, I have an ideal switch. So ideal switch is consuming nothing, almost. These resistances are very small. We can look at the device, for example, here, the MOSFET device here, data sheet for a MOSFET device. This resistance is what? For this device, 8 milliohms. So if I have 1 amp flowing through 8 milliohms, it's my power loss is what? I squared times R. So I squared is 1 amp. So 1 times 8 milliohms. So it's 8 milliwatts versus 6 watts. Right? You see the difference? So even if I include the effect of the power loss, it's not very significant. Right? You see the benefit? I squared R here versus V times I here. Right? When I'm intentionally dropping 6 volts across this thing, for example. Yeah. So this loss in the low pass filter will have an effect. Of course, it will be a loss. But if I properly design my inductors and capacitors and choose my capacitors, then I can make this loss a lot less than the 6 watts. So I have 8 milliwatts due to my switch, for example, and I have another half a watt due to my low pass filter, versus 6 watts in the other case. Right? So that's something to consider. That's why we add this thing here. And we said, okay, sometimes your load voltage requires some changes. Or sometimes your input power supply, like your input here, the input is not 240 all the time. It's 240, maybe 220. There's a window. We have a contract between us and Kahrama. Kahrama says, my window is plus minus 10%. You have to live with that. Right? But if you are developing a design that requires high precision voltage delivered to the load, to live with that, your power supply has to accommodate the plus minus 10% and convert that to something that you can control precisely at the output, right? That's the power converter's function in that case. And that's where it's important to control the switch. So there will be a control circuit and a gate drive circuit, right? So we will see that in our project as well. You will have both to some extent. And we will not be using ideal switches. We'll be using real switches, of course, to do this job. So these switches are different types. The simplest type of switch is a diode. You've studied that before many, many times. We'll briefly go over that. So how does a diode function? If I supply positive VD, if this is the polarity of VD, if I'm supplying positive VD and current is flowing in this direction due to the circuit, right? So a diode, it turns on and turns off because of circuit conditions, right? Can you control its turn on and turn off? You cannot. If you put it in a circuit that satisfies certain conditions, then it will turn on. If that circuit is not satisfying its turn on conditions, it will be off, right? That's what a diode. The turn on condition is ID being positive and VD being positive. That's the turn on condition of the diode. The diode will turn off if you apply negative VD. So forward biased when ID is positive and reverse biased when VD is negative. So if you put VD negative across the diode, it will turn off, right? And I think in 370, you were studying, how these diodes, the depletion layers, all that kind of stuff that I don't know too well. How does the diode function? So when the diode turns off, and you have, let's say, look at, for example, this circuit. You have a simple circuit here, switch, which in this case, let's say we'll put a diode, and you have a resistor here, or an inductor. Okay. Is this voltage more positive than this voltage or not? It is. So is this circuit going to allow current to flow, or is the voltage here on this side higher than this side? Here I don't have a voltage source, right? So there's no reason for not being able to push voltage from this side to this side. Here I have no voltage, for example. Here I have voltage power source, right? So I will be able to push voltage from the higher voltage side to the lower voltage side, and current will flow in this direction, right? So initially, again, inductor initially is a what? Open circuit or short circuit?
Inductor open.
Initially,
It's just short. So
so VL is equal to L di by dt, right? So an inductor, for you to have voltage across an inductor, you need time varying current. So if you supply DC current to an inductor, it will become a short circuit, right? So initially it's an open circuit because it's not behaving as an inductor, it's just a wire. So it will consume some current, a little bit of current, and as an open circuit, then it will be a short circuit. It will be consuming a lot of current out of it. It will look like a short circuit for the DC supply, right? A short circuit for DC. So it's as if you have a short circuit across a battery. So current would want to flow. So if current wants to flow because you have a low impedance here and you don't have a voltage opposing this voltage, right? So, and this node is higher in voltage than this node, so this is a good condition for this diode to conduct, correct? So this diode conducts. How about if I add a voltage here that is higher than this voltage? It will not conduct. So if it's not conducting, it's an open circuit. If it's an open circuit, what's the voltage across the diode? And then this is VDC2, for example.
It's an open circuit.
Yeah, it's an open circuit. What's the voltage across the diode? VDC minus the difference in voltage between the two sides, right? Or if I didn't have this one here, then it would be VDC, right? So it will block the voltage across it, right? So it will block the voltage across it if it's not conducting. This conversion from conducting stage to blocking stage, the physics is what happened in 370, right? Depletion layer, electrons moving to the other side. That's when you have a gap, for example, in the diode, in the silicon layers of the diode, and then when the diode would like to conduct, electrons move across the depletion layer so that you create current moving, right? And then when the diode starts to block, what happens? This depletion layer, you have to build it up again. So initially you have a depletion layer when the diode is blocking. This depletion layer is opposing the current flow, the voltage, the current to flow between the two terminals. Then when you flip the voltage or you're pushing current through the diode in a certain direction, the depletion layer becomes very small and electrons start moving back and forth through the depletion layer, through this zone here, and you can conduct. For you to block after you were conducting, you have to remove all the charge. There were electrons in the depletion layer. So you sort of have to remove the charge from the depletion layer for the diode to block. And this is resembled in this area here. So the diode was on, current was flowing through it. When the diode is off, current does not flow. So here the diode was conducting, here the diode is blocking. For you to go from the conducting state to the blocking state in the diode, you have to remove the charge that's in the depletion layer. So the way you would do that is, or the physics that happen, what happens is a negative current will flow. And we will talk about that more in next class and its effect. Yeah. So we'll stop here and we'll continue next class.